Well, hello everybody. Welcome to today's VGEM meeting. My name is Adam Kellerman, and I wanted to make sure that everybody has had a wonderful meeting so far. And I want to point you to the VGEM website where we have links to the Slack channel, and there you'll find specific, to the Slack workspace where you'll find specific links to the Slack channels for this morning's plenaries and also for the sessions that occurred yesterday. And so without any further ado, I wanted to hand over the floor to our student moderators, Austin Brenner and Rachel Rice, who will be introducing our first plenary speaker.
Thank you, Adam. Hello and welcome to the Solar Wind Magnetosphere Ionosphere Interaction tutorial session. My name is Austin Brenner. I'll be introducing the speaker today. And co-moderating with me is Rachel Rice.
Hello, I'm Rachel Rice. I'm a final year graduate student at Embry-Riddle Aeronautical University, and I'll be fielding questions, so go ahead and drop those in the Q&A section whenever you have them for David. All right.
Our speaker today became an AGU Fellow while at the Applied Physics Laboratory, receiving the AGU Masel-Wayne Award in 1992. He actively participated in the Czech, Russian, and Slovak Prognoz and Interball spacecraft programs, ultimately receiving a medal from Charles University in Prague for his services. Upon moving to NASA Goddard in 2002, he served a 2-year term as Deputy Program Scientist, setting up and running the Living with a Star program. His work as project and mission scientist has focused on the Themis Artemis Explorer and the Living with a Star Van Allen probe missions. He is the TRACERS mission scientist. In recent years, he has taken on the leadership of a cross-disciplinary group, prototyping a wide field of view soft X-ray imager with applications for solar wind magnetosphere and solar wind planetary applications. Nevertheless, community service and research remain at the core of his interests. He is a past president of AGU's Space Physics and Astronomy section, and of course, he has held a position as one of the GEM Steering Committee chairs from 2011 to 2013. Without further ado, I'm pleased to introduce Dr. David Sibeck.
Thanks very much. It's a pleasure to see all of you here this morning. Let's see if I can get my screen to show. Okay, I think you're seeing my screen now. I hope you are. If not, let me know. Today, I'm going to talk to you about dayside solar wind magnetosphere interactions, and I hope to give you a sense of the enthusiasm which this field of research can generate. So we're going to be looking at the day side of the Earth's magnetosphere, and I'm going to begin with some motivation for studying this topic, and then we'll go through it region by region, perhaps looking at some of the highlights or most interesting things, at least in my opinion, for each region. And then we'll have a brief summary at the end looking forward, because the future is equally bright for those who study this part of the Earth's magnetosphere. There are many exciting missions coming along. So one reason for studying the physics of the dayside magnetosphere or the dayside interaction is because you're interested in fundamental processes. And one of those fundamental processes is particle acceleration. That certainly occurs in and around the vicinity of the bow shock, and worthy of study in and of itself because of its basic nature to plasma physics. Another basic phenomenon that occurs in this region of space is reconnection. It occurs at the magnetopause, but it also occurs in the magnetosheath and perhaps even in structures upstream from the bow shock. Yet another fundamental process, one that magnetospheric physicists, at least side magnetospheric physicists don't think about too much, is ion-neutral interactions. And they most definitely do occur on the day side between the Earth's exosphere and between the solar wind plasma or the magnetospheric plasma. And so that's yet a third reason for studying the day side, is a third basic interaction that goes on. And these are themes that will run throughout this talk, and so I'll harken back to them periodically as we progress. Those aren't the only reasons for studying dayside magnetospheric physics. You can perhaps think of some of the unique features of heliophysics that are very well expressed in dayside interactions. One is the cellular nature of plasma structures. There are vast regions of space with rather uniform characteristics, and they're delimited by rather sharp boundaries where very interesting things happen. And those sort of things certainly happen. Cellular structures present in the solar wind and the magnetopause and the bow shock are examples of very sharp structures. So it's very common. It's a unique feature of our discipline, one that other disciplines don't have. Teleconnections is another unique aspect of our subject. Who would have imagined, if you look over here at the right, that a burst of reconnection at the magnetopause could excite something interesting happening far, far away, many tens of Earth radii away in the Earth's ionosphere. Teleconnections are real in our subject. In other subjects, they're open for discussion or don't exist. But in magnetospheric physics and heliophysics, teleconnections are common occurrence. Things happen remotely at a great distance. Cross-scale interactions, another unique feature of our discipline. Things that happen on the tiniest of scales, on electron gyro radii, like reconnection at the subsolar magnetopause, can ultimately lead to a complete reconfiguration of the Earth's magnetosphere, placing boundary layers and plasma regimes in different places, changing the size and shape of the magnetosphere. All of these are good reasons and fascinating topics to study in dayside interactions. Yet another reason to study dayside interactions is the key role that the dayside interactions play in the system science of the magnetosphere. The energy that powers geomagnetic storms and substorms, big space weather effects, originates in the pristine solar wind, but is modified, diverted, and are focused to enter geospace by crossing through the foreshock and bowshock, passing through the magnetosheath, entering somewhere across the magnetopause and down into the cusps, and flowing down all the way down to the high latitude dayside ionosphere. So by studying what's going on in each of these regions, which I've numbered here and which we'll be talking about during this talk, I can learn a bit more about the nature of that interaction, either in situ or remotely. So I'd like to start where it all begins for the magnetosphere, at least for the majority of processes in the magnetosphere, and that's in the solar wind. And why should we study the solar wind? Well, it's a driver for many geospace phenomena, for example, storms and substorms. There is a great review article by Joe Borowski, which I would like to refer you to. What I have time to talk about today a little bit is the solar wind at solar max and solar min, and the control parameters that it exerts on the magnetosphere, and triggers in the solar wind, and how confident we are, or how unconfident we are, about whether they come to the Earth. This beautiful picture on the right shows a kind of cellular or spaghetti structure of the solar wind, as illustrated by Joe Borowski in that article. So here are two plots showing various solar wind plasma and magnetic field parameters. On the left is solar maximum, on the right is solar minimum. What you get is a full year of data in both cases. And you might initially say, well, gee, they look about the same. What's the difference between solar maximum and solar minimum? And the answer lies in the scales of these plots. Just all of these features, the variations in magnetic field and in plasma parameters, are just so much bigger in solar max than they are in solar min. So that's solar maximum. You've got very strong drivers for magnetospheric phenomena. And I've put this in because I want to contribute this talk to a permanent record. It shows you histograms of solar wind parameters during solar wind and solar maximum and solar minimum, and it shows you averages and standard deviations, but that's not the key point. The key point which I want to talk about is just about anything you can think of in the solar wind is for some phenomena in the magnetosphere, and we're going to talk about those today. For example, the spiral or orthospiral or some other orientation of the IMF, that determines where the foreshock is. The north-south orientation of the IMF can help you determine where reconnection occurs on the magnetopause. The electric field in the solar wind might determine the strength of the interaction. The velocity of the solar wind might tell you whether the Kelvin-Helmholtz instability will occur on the magnetopause. The shock numbers in the solar wind determine the shock location and strength. Plasma beta might inhibit reconnection. The flux of solar wind ions is a key parameter determining how much charge exchange with exospheric neutrals goes on. The solar wind dynamic pressure tells you where the magnetopause is, and the ratio of heavy ions to protons has an important factor in determining where X-rays are generated. We'll talk about these all a little bit more in future. This sort of gives you a guide to where I'm headed. So solar wind input really matters. It may come as a surprise, but there are still people alive today who remember a time when there was no L1 monitor. That was pretty difficult. You didn't know what the input was. Nowadays, you can always find L1 observations. In fact, confusingly, sometimes you can find L1 observations from more than one spacecraft, and it's difficult to know which one to use. And before we get underway talking about the magnetosphere, I'd like to see just how confident we can be when you take these L1 monitors to determine the magnetospheric response. And we'll look on 3 timescales: geomagnetic storms, a timescale of days; substorms, hours; and looking for triggers for flux transfer events and substorms on a timescale of minutes. So it may come as a surprise to you, but L1 monitors are not usually directly upstream of the Earth along the Sun-Earth line. They follow these kind of circular paths, hovering around the L1 libration point upstream, and they spend most of the time, let's see if I can find the point, they spend most of the time way off the Sun-Earth line, as this histogram of position shows. If they were right on the Earth-Sun line, they'd be here along this dashed line. Usually they're far off that dashed line. So they might not see what you want them to see coming to Earth. Let's go back. There we go. Okay, so on storm timescales, you're pretty safe. Why would I say that? Because there are these different models predicting the occurrence of geomagnetic storms, and for any given solar wind input, they kind of get the general sequence of DST right, which means that they're getting the storm prediction correct. The differences probably depend on the model rather than any problem with the solar wind input. So over long timescales and for big events like geomagnetic storms, no trouble with your solar wind monitor. How about on hour timescales? If you're looking for an hour or two of southward IMF orientation to see if there'll be a substorm, will you get it? Well, it's pretty good, as this correlation trace between wind and ACE shows. BZ is pretty well correlated on hour averages. But there are some problems if you look a little bit closer. You might think, based on wind observations, that IMF BZ is 0, when ACE says it was plus or minus 4 nanoteslas. Maybe that's okay. Maybe you don't mind that. How about on minute timescales? There, the scatter looks even worse, big scatter. Now, if you think the IMF is plus 10 nanoteslas, in general, from one spacecraft, the other spacecraft says it's also about plus 10 nanotesla. But how about if you thought it was 0? There's a big spread in what it might really be if ACE is the one that's really seeing what the input is, and wind is the one that is what you think the input is. Maybe those discrepancies bother you. Maybe they don't. I don't know. How about correlation lengths? Here, plasma and magnetic field parameters have been correlated over different scale lengths in the solar wind on using minute data, and the correlation coefficients are only 0.6 to 0.7, which means you're only explaining 36 to 49% of the solar wind variability. So if you're looking for a solar wind trigger and you're using a monitor at the L1 libration point, there's a good chance you're going to miss it, or you're going to pick something that didn't really come to Earth. It's a risky business. These are the scale lengths for solar wind features that were derived by Richardson and Paularina in this study. And these distances are comparable to those that L1 monitors lie off the Sun-Earth line. Okay, let's move a little bit closer to the Earth. Why did we study the foreshock? It's a great place for particle acceleration. And as I'll show you, it dramatically modifies the incoming solar wind. So if you're a magnetospheric physicist, please think about what happens to the solar wind in the foreshock. And I'll show you that in a few slides. Where is it usually for steady state? For spiral IMF orientation, it's usually upstream of the dawn magnetopause. We're going to look a little bit at particle distributions in the foreshock and the waves that are generated there. And we're going to talk a bit about how it modifies the incoming solar wind. So here we go. Particle acceleration in the foreshock. It might be a good investment for you. You stick in 1 keV solar wind ions, or perhaps a little bit higher energy ones, as seed population, and out pop back up to 1 MeV, maybe even greater energized foreshock ions. So something in the foreshock at the bow shock is doing a great job of accelerating a small part of the incoming population. Processes that could occur are specular reflection off the bow shock, Schafter acceleration, whoops, or diffusive Fermi acceleration. Good review by Dave Burgess in 2012. And a small fraction of those incoming ions and electrons really do get energized. We now have global hybrid code models that can predict self-consistently the particle distributions, in particular the Vlasiator code in Finland, but other codes are available, showing incoming solar wind and foreshock ions, really cool, and how they interact with each other via waves to produce diffuse or other types of distributions in the foreshock. What does the foreshock do for the magnetosphere? Well, amongst other things, it generates waves by interaction of solar wind ions with reflected ions. And it bathes the magnetosphere in those energized particles. And here's an old figure showing which regions of the magnetosphere lie behind the quasi-parallel bow shock. That is the regions to which these waves or structures or particles in the foreshock can reach at the magnetopause. So these global simulations can actually be used to predict the waves in the sheath. Some of the waves are generated in the foreshock like here. Others are mirror mode waves generated in the magnetosheath. The magnetosheath and the foreshock are just full of waves that are going to impact the magnetosphere. And here's a recent run comparing observations with simulations of those waves being generated in the foreshock. Can't find my pointer. In the foreshock and propagating through the sheath and getting into the magnetosphere. Cool stuff. Whoops. Okay, these waves and the energized particles, they're not negligible if you're a magnetospheric physicist. Sure, those energized particles in the foreshock are few in number. They're not that big a percent in density of the solar wind population, but they're energetic and they have a high temperature, and therefore they exert a large pressure on their environs. And what happens is they excavate giant diamagnetic cavity in the magnetic field strength and density. And here's an example, a burst of foreshock ions, and it's excavating a cavity in the magnetic field strength. It's excavating a cavity in the density in the foreshock. And that it's the excavated properties, it's the modified solar wind that's actually going to come and hit the magnetosphere. So it's important to know about that. How big of an effect could it be? Well, here's a paper that says during a period of radial IMF, the magnetopause expanded 3 Earth radii outside of its typical position. Well, that would be an 80% decrease in solar wind pressure. So this is a big effect. The foreshock should not be ignored. And you'll ignore the foreshock at your own peril if you're seeking to understand the solar wind magnetosphere interaction. It generates big pressure changes on the magnetosphere, sometimes localized, sometimes global. There are a lot of wild animals. This is a very recent years have been a prolific time for studying transient events that are generated in the foreshock. Some of these transient events are generated when IMF discontinuities strike the bow shock, hot flow anomalies. Some are generated by IMF discontinuities entering the foreshock. Some are located between IMF discontinuities. Some of them occur without discontinuities. These events upstream in the foreshock have their own local transient big effect upon the solar wind magnetosphere action, and in particular upon the magnetosphere. Here's an example of one, and perhaps it doesn't look too impressive to you. There is a hot flow anomaly hiding in this figure. You kind of see it by the bumps in magnetic field strength and density and the big deflection in flow, which makes it a flow anomaly. But perhaps you're not impressed by that. You think that's just a wiggle, but look what it does to the magnetosphere. Those sort of events can drive 5 RE amplitude waves on the magnetopause boundary. That's pretty big. And those waves propagate anti-sunward with the solar wind. Big effect. Magnetosheath. Why should we study the magnetosheath? It provides outer boundary conditions for the magnetosphere. It's a place where ion-neutral interactions readily enable remote sensing of the boundaries and plasma characteristics of the magnetosheath, and it happily transmits and generates new interesting structures and waves that move from the foreshock through the sheath to the magnetopause. Where are we now? Wonderful statistical studies of magnetosheath plasma and magnetic field parameters exist. There are missions in the past and in the future to remotely sense the magnetosheath. Those who love waves find it a wonderful place to study various types of waves, and there are very interesting transient events that occur in the sheath. Let me summarize those. Here are just some of the beautiful pictures that have originated from work presented at GEM and done in the past few years. These pictures on the right showing statistical patterns of plasma parameters in the magnetosheath, in the outer magnetosphere, are just a fantastic way to visualize the solar wind magnetosphere interaction. When you look in details, sometimes you find striking dawn-dusk asymmetries in the various parameters in the magnetosheath. Lots of physics to learn from those. Ion-neutral interactions. The magnetosheath is a place where solar wind plasma meets exospheric neutrals. And when that happens, they often exchange electrons. And when they exchange electrons, the solar wind ion goes shooting off as an energetic neutral to distances far away, enabling remote observations. Some of the most spectacular results seen at the GEM meeting and seen in the past few years come from Ibex observations of ENAs. You can actually remotely sense the inner and outer boundaries of the magnetosheath from energetic neutral atoms seen many tens of Earth radii away. You can remotely sense the cusp, another topic that we'll come to in a few minutes. And in more recent years, there's been a lot of effort generated towards remotely sensing the magnetosheath in soft X-rays, because when high charge state solar wind ions meet exospheric neutrals, they also exchange electrons, and that exchange of electrons can result in the emission of soft X-rays. There is as yet no wide field of view camera looking at the magnetosheath to see these emissions, but narrow field of view astrophysics missions have seen them on multiple occasions. They're always there, and ultimately, when such a mission flies, and such a mission is scheduled to fly, as I'll talk about in future, we will be remotely imaging the sheath in soft X-rays too, and the cusp in soft X-rays. What about waves in the magnetosheath? Spectacular simulations coming out from global hybrid codes. You can see mirror mode waves throughout the dusk side magnetosheath generated by temperature instabilities. Over on the dawn side, that's a more likely place for foreshock waves to be transmitted through. The temperature anisotropies that you need to generate the waves are there. The beta is what you'd expect. There are also bow waves that encircle FTEs as they move along the magnetopause. Here's an FTE that's moving, and here's a bow wave that it's sending out in front of itself as it moves poleward and northward. The magnetosheath is an interesting place to study for those who like magnetic reconnection. The interaction of a tangential discontinuity with the bow shock may compress the discontinuity, squeeze it, turn reconnection on. And here's a paper by Taifan showing the reconnection jet, showing the electric fields with plasma moving in and showing that this was a tangential discontinuity. Cool phenomenon. Transients, all of those features I mentioned in the foreshock region, they're transmitted through the magnetosheath. Here's an example of one transmitted into the magnetosheath reported by Shafrankova et al. This is a hot flow anomaly from the upstream region, pushed through the bow shock and transiting the sheath. So you have every reason to believe that that's going to ultimately come to the magnetopause. And a pet peeve at the bottom, a lot of journals are archiving themselves in black and white, and you can see what that does to color spectrograms. Bad idea. Also, new features in the magnetosheath, features that were not present in the upstream region, that were not in the foreshock. So the sheath is a veritable zoo of transient events that are coming towards and about to smack the magnetosphere. One example of those are magnetosheath jets, as proposed by Heli Heitala at a GEM meeting. She was a regular GEM participant. And what happens is there are ripples in the bow shock, and those ripples launch high-speed jets, which propagate into the magnetosheath. Fantastic picture of that happening over here from Karimabadi. Jets are moving along streak lines through the magnetosheath, and they're moving so fast that they have a bow wave in front of them as they approach and strike the magnetosphere. Cool, really cool. Finally, the magnetosheath is a loss region for magnetospheric particles. One of the most fascinating simulations I've seen in the past number of years comes from Karim Soratia at JHU APL. He launches blobs of protons and oxygen and electrons on the night side and watches them drift around the magnetosphere. Some of them succeed in traversing the day side magnetopause. Others go smack into the magnetopause, and those particles are lost to the sheath. Very interesting to see where and when they're lost and where they go. Magnetopause. Why study the magnetopause? It's a gateway for solar wind energy to enter the magnetosphere. It's a super place to study reconnection physics. There are an abundance of transients there. The sort of things we think we know, but do we really? Are where is the magnetopause? And the sort of things that are hot topics right now, are, as always, are transients and flux transfer events and the Kelvin-Helmholtz instability. Do we really know where the magnetopause is? Here is an old paper from Shu, 97, comparing their predictions of where the magnetopause is for solar wind dynamic pressure and BZ with those that Roloff and I got many years ago. Sometimes the predictions are similar, and sometimes they are strikingly different. Look at these two panels. This panel here should look like that panel there. Obviously, there's a gross discrepancy. What we usually try to do is determine the magnetopause location using hourly average solar wind parameters of the solar wind dynamic pressure, IMF-BZ, and sometimes dipole tilt angle. But since the magnetopause lies at rest where magnetosheath and magnetospheric pressures balance, and magnetospheric pressures are mostly magnetic, and magnetic pressures are due to magnetic fields, and magnetic fields are due to currents, it might be better if we were looking at magnetopause locations as a function of the Chapman-Ferraro current strength, or the region 1, so the ring current, or the cross-tail current. And all of those have different response times to solar wind variations, ranging from minutes to hours. So it's a complicated business, and you've got a lot of work to do if you're really going to predict the magnetopause at any given time. Here's an illustration of the ring current. Ring current enhances magnetic field strengths in the outer magnetosphere. The cross-tail current depresses them. The region 1 currents depress them. They're all varying with their own time scale. They all have their own effect on the magnetopause. It's not so simple as to just pick an hourly average solar wind variable. So as a result, there's still plenty of scatter in where I say I predicted the magnetopause, but there's a lot of scatter in where it really occurred compared to where you predicted. And we need more studies comparing simulations and observations, because right now we don't really know where the magnetopause is. We think we do, but we don't. What about the magnetopause and reconnection? Basic questions you might ask are, where does reconnection occur? How does it occur? What are its spatiotemporal properties? A lot of people in the olden days, and I'm an old timer, talked about the component reconnection model. And there was another model called anti-parallel. And now a model which seems to do the best job is kind of a mixture of the two, a little bit different principle, the maximum shear model, which tells on the magnetopause where you think reconnection should occur. There's some regions where the fields are anti-parallel, maximum shear, but they're also connected by a line passing through local nodes. So maybe everybody had something a little bit right. This model has been advocated very successfully by Karl-Heinz Trattner at numerous GEM meetings. We cannot omit to mention the pioneering work that MMS is doing on reconnection microphysics with a guide field and without a guide field, looking at the acceleration that occurs, the currents, the fields, the types of electron phase-space density distributions that occur. Very detailed work helping us to understand this microphysics process, which governs the overall interaction. Now, reconnection could be steady or unsteady. Here's a paper which said it was steady for hours, and they deduced that, Harold Frey and Taifan, by looking at remote images of the cusp dayside aurora and seeing a cusp auroral spot that stayed present and at a similar latitude and longitude for many hours at a time. So reconnection could be steady and balanced. Whoops, go forward. Of course, we also have reasons to believe it's unsteady. The IMF orientation is always changing, and we know a southward IMF will turn on reconnection and erode the magnetopause. Some people believe that each individual southward IMF turning triggers a burst of reconnection. That viewpoint was advocated by Lockwood many years ago. Other people can't find the triggers, but they can find the transient response, and therefore they conclude that there are no triggers. Reconnection is intrinsic. It's intrinsically unsteady at the magnetopause. One possibility is that turbulence in the magnetosheath triggers reconnection. Here is a global hybrid run by Nick O'Meady, where he keeps all the turbulence and he sees lots of FTEs. Here's one where he takes an eraser and rubs out the turbulence, only one FTE at the same time in the simulation. So maybe lots of little individual turbulence and wiggles and waves were triggering bursty reconnection localized at the magnetopause, maybe. But here's a simulation from Jimmy Rader, no turbulence in this global MHD simulation, and yet there are transient events, flux transfer events, bursts of reconnection that occur periodically in this simulation. You don't have to have turbulence to trigger reconnection. How big are these flux transfer events, and what is their topology? It's an open question. Here's the original picture of a flux rope with a dimension of about an Earth radii. Maybe it's a true flux rope with many Earth radii, or maybe it's a bubble extending over many Earth radii. Lots of possibilities. How long indeed is the reconnection line? Here is a deduction based on two dawn side observations of a reconnection line that occurs from the night side all the way to the subsolar point. That, of course, is an extrapolation. We unfortunately, at the present time, don't have multi-point observations capable of telling us where and when the reconnection extends, although people have used ground-based and space-based measurements. Zhu, for example, has worked on this problem. It's an open area of research. How big is a reconnection line? Do reconnection lines grow with time? In this early work by Lockwood, it was assumed that a reconnection line could appear suddenly over 4 hours or more in local time and produce an event just like that by snapping your fingers. Other papers like this one by Steve Milan attribute reconnection to some process that grows along the magnetopause, along the auroral oval, and continues after an initial burst. Maybe. Why would a reconnection line grow? Well, perhaps because some IMF discontinuity is coming in, touching off reconnection, and as the discontinuity moves to touch other parts of the magnetopause, reconnection spreads, maybe. Or maybe it grows at some Alfvén speed that propagates away from some initial disturbance. Or maybe it spreads at the speed of current carriers like ions and electrons. This is another hot topic of research pioneered by Zhu and co-workers. In any case, reconnection erodes the magnetopause. We all know that the dayside magnetopause moves inward when the IMF turns southward. We could ask the question, well, how fast? How fast does it move in following a southward IMF turning? Well, if reconnection were on the dayside were balanced by that in the magnetotail, the magnetopause wouldn't even move inward at all because all the flux eroded would be immediately replaced. But if it isn't immediately replaced, the magnetopause might move in very quickly. Dayside magnetopause moves closer to Earth quickly or slowly, or it might move in steps, each step being the removal of flux by 1 FTE. What do global MHD simulations tell us? Well, I've only looked at one, and in this simulation, the magnetopause following the onset of a southward IMF turning first moved in quickly and then more slowly. And then the inward motion came to a complete halt because a substorm occurred on the night side and pushed a whole bunch of flux back to the day side and pushed the magnetopause back almost to where it started. I don't know if that's typical or not. And those timescales are right. It's an open area of research. My favorite picture in this talk, Kelvin-Helmholtz waves, surprisingly far more prevalent than anyone would have thought. And here they are, ripples on the flanks of the magnetosphere, ripples that Cavosi and Rader reported were present far more often than anyone would have thought, almost always. Down to the cusps. Why should we study the cusps? They're a pathway for solar wind energy to enter the magnetosphere. They help us learn about reconnection physics. They have plenty of transients in them. In steady state, we've got a pretty good grasp on where they occur, and the transients, there are lots more to be learned there. So where is the low altitude cusp? From statistical studies, for example, of DMSP, we know that the cusps are within 2 hours of local noon at about 78 degrees magnetic latitude. Here's some more statistics on them about your probability of seeing them as a function of local time here on the left, the latitude that they occur at as a function of IMFBZ, their latitudinal range, a couple of degrees, 1 or 2 degrees. Big statistical studies, plenty of data to execute them, high confidence. Let's see if we can go on. Whoops. We also have a pretty good idea about densities in the cusp. They track those in the solar wind, so that's good because the plasma in the cusp should come from the solar wind. Spectacular study by Benoit Leroux of cusp plasma parameters on the basis of cluster observations. He also did magnetic field parameters there. You can see the plasma there, and in his study you can see where it's accelerated, and which way it's going, and how it's penetrating. Cusp moves equatorward following southward IMF turnings, got it. Here are 3 cluster spacecraft observations of the cusp at successive times. Clearly the cusp moved from high latitudes to low latitudes, so things change in the cusp as a function of time. They might also be spatial. What do we not know about the cusp? We don't have any instantaneous global picture. We don't know whether reconnection occurs at single or multiple locations, and we're not sure whether reconnection is steady or unsteady. Here are some cartoon predictions for cusp density and emission structures from Weiss, 1995. Various IMF conditions, reconnection occurring at 1 or more locations, creating structures that extend in azimuth and latitude, might be diagnostic. If you could take pictures of the cusp and see these, we want to take pictures of the cusp. We want to distinguish between different models for time-dependent and spatial structure in the cusp. And the good news is we're in about to be able to do that. The Cupid CubeSat will launch this September. It will look upward into the cusp and take snapshots of the density structures there in soft X-rays emitted by solar wind, high charge state solar wind ions interacting with exospheric neutrals. That's the remote sensing or optical mission that's coming up. But there's also an in situ mission coming up. That is the Tracers mission. 2 spacecraft will fly through the cusp, one after the other, checking out whether there are spatial or temporal structures there. Gonna be cool. The future for cusp studies is wonderful. So last topic, dayside high latitude ionosphere. Why study this? We can use ground-based measurements in the high latitude ionosphere to study solar wind entry into the magnetosphere. It's a great place to remotely study reconnection physics and transients in the solar wind magnetosphere interaction. We have a whole array of observatories there, which include ground radar, magnetometer, rheometer, and all-sky imagers that can help us reach our conclusions. There are lots of cool transients. I just have one slide. I'd like to mention that for me and for GEM, this is where GEM began. One of the first campaigns at GEM was to look at ground-based observations and deduce the nature of the solar wind magnetosphere interaction from them. On the left, you see how magnetometer observations can be combined to deduce traveling convection vortices. Perhaps they're due to pressure pulses. Perhaps they're due to the Kelvin-Helmholtz instability. Perhaps they're due to flux transfer events. Whoops. Oh, let's go back. All sky imagers, really cool features. There's a wealth of information in all sky imagers, far more I know from talking to Briggs, who was a summer student at Goddard, far more than have been reported in the literature. Very wealthy data set, full of interesting events. Super Darwin ground radar showing FTEs moving up into the realm of endeavor with much more work to be done. So that brings me to the last slide. What is the future for dayside interactions? Well, there certainly are more questions than there are answers, and that's a wonderful thing. It's a vibrant area of research. We're entering a time when global MHD and hybrid code models are going to be available at your request. That is going to make it spectacularly exciting because they will make predictions that observational people will test, and they will go out to see if they can simulate what observers report. The role of the exosphere is becoming more clear and more important. We've got a forthcoming mission, another mission coming up, the GLIDE mission, which is specifically going to tell us the properties of the exosphere from an L1 vantage point. Pay attention to that interesting mission. We've got these two CUSP missions coming up, Cupid and Tracers, that are going to define the nature of reconnection, one by remote sensing, one by in situ measurements. The existing missions like Cluster Themis and MMS, their orbits continue to evolve. There's new configurations that will help us better determine the properties of the outer magnetosphere. There's an opportunity for future missions to construct constellations and have multi-point simultaneous measurements that would likely employ CubeSats. There are immense prospects for global imaging in EUV, FUV, ENA, Lyman alpha, Thomson scattering, and soft X-rays to look at the plasma structures that are out there. So it's really a wonderful time to come. And last, I'd like to mention a recent review on this topic, Dayside Magnetosphere Interactions, an AGU monograph by Zhong and Zhang, which came out last year. And that's it. Happy to hear any questions.
Thank you, Dr. Sibeck. That was a fantastic talk. We've got a few questions in the Q&A. We'll start just with the ones that are here at the top. So from Drew Turner, what are the integration times and spatial resolution for soft X-ray imaging of the magnetopause and sheath? And how much is the magnetopause expected to move during those integrations?
Okay.
What about line of sight projection effects?
Okay, so first topic, a notional or nominal integration time for a soft X-ray imager of the magnetopause and magnetosheath, for example, 30 Earth radii from the Earth, would be about 2 minutes. But in general, soft X-ray imagers like that on Cupid or the one on SMILE return individual counts. So on days when more X-rays are generated, i.e. days when the solar wind flux is higher, then the integration time can be less, perhaps even as small as 15 seconds. So the bigger the solar wind disturbance, the shorter the integration time, and or the better the spatial resolution with which you construct pixels. There are line of sight effects, and the interesting thing is that the dominant source of X-rays along a line of sight comes from the tangent to the magnetopause, because that is the closest approach to the Earth, the deepest position within the exosphere, and the place where the neutral densities are highest. And that is therefore dominates the entire line of sight. And the amount the magnetopause moves, magnetopause motion, you probably would not want to you might not want to try to track Kelvin-Helmholtz waves on the magnetopause, because you might have tens or hundreds of kilometers per second magnetopause velocity, but 10 kilometers per second or 20 kilometers per second when you're trying to find spatial features that are an eighth of an RE or a quarter of an RE. That's not going to make too much trouble for that.
All right, moving on. Next question's from Michael Hardinger. Hi, David. Do you think we'll ever get to a point where we can predict, even roughly, large magnetopause perturbations caused by foreshock disturbances, similar to what can be done for IP shocks with L1 data and numerical simulations? Could this be done with imaging, remote sensing, L1 data, etc.?
Well, first of all, it's my personal belief that using L1 data, I've seen so many cases with a lack of success of what came to the magnetosphere, that an in situ L1 monitor is never going to be 100% and may not even be anywhere close to 100% in predicting these big disturbances. On the other hand, we can't simply put a spacecraft at x equals 30 of the magnetosphere and leave it there. It won't stay there. So we can't do that either. If we went to imaging, we could image what's coming in, but then that wouldn't be so much, I mean, image in the solar wind looking from the side or the magnetopause, but then that would be a nowcast rather than a forecast. We'd be seeing the big change as it happens. So I think there are always going to be rogue events that we couldn't predict going on.
Okay, and then we've got another follow-up on that. Considering the importance of space weather and solar wind driving of the magnetosphere, ionosphere, thermosphere system, do we need a dedicated solar wind monitor inside of L1, for example, at the cislunar space?
Okay, so let's go back, let's ponder the slides I showed. If your objective is to predict a substorm or a geomagnetic storm, you can do pretty well with the hourly averages upstream. The correlations were not too bad for that. You'll miss some of them. But if you're interested in transient events, then the situation is a lot tougher. But to put a monitor direct, well, okay, so what you could do is you could have a lot of spacecraft up there, a constellation of maybe 3, 4, 5 going around a circle around the Earth at 30 RE. Imagine having 5 IMP-8 spacecraft at distances of 30 to 40 RE, so that one of them was always upstream. If you truly thought that transient events were important and triggers for the solar wind interaction, that would probably be the way you'd approach it. They would take turns, each one of them taking turn as a sentinel as they go around the Earth.
Okay, and then we also have a live question from the audience. Joaquin Byrne, I believe. I think we're going to get their mic unmuted so they can ask directly.
Okay, super.
You should be able to unmute now and talk.
Joachim, are you there?
Sorry, that was me. I think I just pressed it by mistake.
Well, I'm glad to hear from you anyways.
Yeah, so glad to see you. So very nice talk.
Thank you.
Well, then we'll go back to the Q&A. We've got a question here from Bill Latko. For quasi-steady IMF solar wind conditions, does the transient nature of reconnection or its degree of transience depend on IMF orientation?
I don't know the answer to that. That's an open question. I'm going to try to repeat that question back to make sure I understood it. If the IMF is steady, is there a preferred orientation for transients to occur? Certainly a steady northward, we're not going to see much happening on the dayside equatorial magnetopause. A steady southward, we are likely to see lots of FTEs, which someone might claim is due to an intrinsic instability, and someone else might look for small fluctuations in the southward IMF to see, or turbulence generated. So I think there's room for a lot more work on that subject.
Okay, I think we've got time for one more question from Jason Durr. Absolutely love the talk. Are there any general pedagogical comments you have about how the variation in magnetopause boundary location in response to solar wind pressure affects the predictive utility of L1 orbit measurements?
Oh, I've got to think my way through those words. Well, could you repeat that question again?
Sure. Are there any general comments you have about how the variation in magnetopause boundary location in response to the solar wind pressure affects the predictive utility of L1 orbit measurements?
I think my short answer is no. I think this is an open area of investigation that someone should take the big list of crossings that we have right now, the various global models that we have, the solar wind input from different L1 monitors, and see just how well we can do. And I've talked to Jari Collado-Veda, who works at Goddard in the CCMC, and it's not a very pretty story, and we're not that successful. Sure, everyone agrees the southward turning erodes the magnetopause. Everyone agrees a pressure increase moves it in, but exactly where it is, there's considerable disagreement between models and observations. And that might be because we're missing some of the control parameters. It might be because the models need a bit more work. It might be because the upstream monitor's in the wrong place and not doing it. And it might be this idea that I can bin everything by hourly averages of solar wind parameters. Maybe that's wrong. Some things respond quicker than an hour. Some things take more than an hour. There's a lot of work to be done there.
Okay. I think we've got a little more time, so we'll ask another. This is from Manhua. Hi, David. Thanks very much for the great talk. Could you please comment on particle heating by waves in the sheath? I'm especially curious whether mirror mode waves can accelerate particles. As a follow-up, are there any waves that can accelerate both ions and electrons in the sheath?
Okay, so by chance, I have come across recently some papers from the cluster mission which show electrons heated to superthermal energies, not astronomically large energies, in mirror mode waves. And if you send me an email, I'll look for the references to those. But that's not energizing them to tens of keV. That's just getting them above the thermal level, and they're in each and every pocket of the waves. And probably the same thing is true for ions too. And the latter part of the question was what?
Are there any waves that can accelerate both ions and electrons in the sheath?
I think there's at least some degree of acceleration by the mirror mode waves of both, but not usually those accelerated particles are attributed to processes at the shock and then convection downstream into the sheath to higher energies.
All right. This is the last question in the chat, but we're still waiting for a panelist. So if anyone in the audience wants to add additional questions, we'll welcome them. But for now, Rebecca asks, can you please comment on the energy distribution of the accelerated ions in the foreshock? Could it be confused with an astrophysical plasma of a similar temperature, or is the energy spread too wide?
Oh, okay. So I would love to talk a little more about this topic. First of all, if you're sitting upstream from the bow shock, you could be in the middle of a solar energetic particle event, and then that distribution of particles goes to much higher energies than can be produced at the bow shock. And so your bow shock generated particles could be superimposed on it, but they have their own spectrum, and they only get up perhaps to 1 MeV for ions and several hundred keV for electrons. They're not coming from another astrophysical source unless they're cosmic rays, and then their energies are even higher. But I do want to mention, in recent years, there's been some continued work going on simple leakage from the magnetosphere. Sometimes you see O+ or He+ ions, and they have succeeded in swimming against the turbulence in the sheath and crossed the bow shock and gotten into the upstream region. And they may be more common than most of us thought until recently. And the way that they are identified is on the basis of composition. If you have an instrument that can actually see O+, that's a good indicator of something that came from the magnetosphere, because the solar wind itself is O6+ or O7+ or O5+. So in short, with experience, you can readily look at upstream events, see that they occur on magnetic field lines connected to the bow shock, see the corresponding waves or turbulence that help generate them, see their spectrum, and see that it's limited to some hundreds of keV or MeV, rule out that they're a solar energetic particle event, and use composition to rule out that they came from the magnetosphere.
All right, thank you. I don't see any other questions in the Q&A, and no one has their hand raised, but we do have one in the chat from Vanya. As a former steering committee chair, what would you consider, or what do you see, what's your vision for the future of GEM?
Oh, okay. I have a few comments. One is originally GEM was predicated on a heavy use of NSF supported resources. And that's why one of the first campaigns was on the high latitude dayside ionosphere. And so I would like to see stronger participation and presence by those making use of ground-based observations, which are an NSF resource. I'd like to see the NSF make a bigger deal out of that to support the financial viability of those ground-based programs. A second topic that concerns me and concerned me even when I was chair of GEM and I did not find a good solution was the ensuring that the GEM would not be a summer fall AGU. Rather, the emphasis should be on discussion, and people should at all possibilities should be encouraged to discuss work that is not yet completed in an atmosphere where they could be confident that that's acceptable to do that. And that new ideas, the balance between discussion and formalized presentations. I got more out of the discussion type activities of that for me is one of the highlights of my GEM career, is informal discussions inside and outside meeting rooms on problems that are not yet solved, on topics where I actually can have a say and influence the course of events or learn something or go off and develop new partnerships. But yesterday there was a session on what GEM means to me. And I have to say GEM has been my entire career. I've been there from the start, 30 years, and it's the highlight of my year. And it is the place where I have made the most lasting friendships and partnerships in my career. So I'll put that in as something that gives me a warm, happy feeling.
Fantastic, thank you. I think we've got one last question from Michael Hardinger. I see your hand raised. You should be able to unmute now. And that will be our last question to David for today.
Okay, great. Hopefully you can hear me. Fantastic talk, David. I really enjoyed it. Great information. Just to follow up on the question I had earlier about predicting and the rogue event comment you mentioned, that we'll never capture these. I'm just wondering, with the current modeling capabilities, like the hybrid kinetic models, if you can really well prescribe the pressure and the IMF and everything at like 30 RE, like let's say you had 30 satellites up there, and you could prescribe it everywhere along like a 30 RE boundary.
Yeah.
Is there still an element of random chance? Like, do you think you would still miss some events? Could you comment on that?
First of all, our models are almost at the level where they can be put to the use you want. The closest I've seen is a 3-dimensional model from Yulin. The Vlasiator model is 2D, 2.5D. The Nicomedes model, 2.5D. So we're just on the edge of even having models to do 3-dimensional global interactions. I think that it's not an element of chance, but you would probably have to have an inter-spacecraft separation of like 20 or 15 RE along a circular path around the Earth, because some of these an edge might not come to Earth, and so you'd have to have a spacecraft at 30 RE from Earth that's within 10 or 15 or 20 RE from the Sun-Earth line to even be reasonably 100% sure that that was going to come to Earth.
All right, thank you. I will turn the mic back over to Adam, and we'll continue with our next plenary speaker.
Thanks, everybody.
Yeah, thank you, Dave, and thank you, Rachel and Austin, for that. I'm going to go straight to our next speaker, and I'll hand the mic over to Riley Troyer and Mike Coughlan, who will introduce Janet.
Hi. Hello, I'm Riley Troyer. I'm a graduate student at the University of Iowa, and I'll be introducing our next speaker. But before that, I will let my co-moderator introduce himself.
Hey everybody, I'm Mike Coughlan. I'm a third-year grad student at UNH, and I'll be handling the Q&A portion of this. So feel free to throw your questions in the Q&A section, and make sure you kind of read through the ones that are already there, and maybe upvote ones you want to make sure are asked, because we can kind of get to those first. So back to you.
All right, so it's my pleasure to announce our special guest for you. Dr. Janet Vertesi is a sociologist at Princeton who's been described as being a Margaret Mead among the Starfleet. That's because she specializes in complex technical organizations, specifically scientists and engineers. For instance, she has studied the inner workings of NASA robotic spacecraft teams and has witnessed 9 planetary missions. In addition, she's authored publications across social studies of science and human-computer interactions. And if that wasn't impressive enough, she also has degrees from 3 different countries and has written 2 books, Seeing Like a Rover and Shaping Science. I hope you're as excited to hear from her as I am. So let's welcome Dr. Janet Vertesi.
Thank you. Thanks so much for that introduction, and I really appreciate the opportunity to speak with you today. So I'm here as a social scientist who specializes in studying science teams. And I'm here to share some of the insights from my field and from my studies that in the last 10 or 15 years, I've realized are actually really of benefit to scientists in trying to understand some of the dynamics that they're seeing in their own scientific communities, particularly as they're starting to dig into the really thorny problems of diversity and representation. And despite the fact that diversity has become a rather large term that has inspired a lot of political commentary, et cetera, that actually from a sociological, social science perspective, there are some things we know about how people behave when they're in groups that are highly regular and highly predictive of certain forms of behavior, and also suggest the ways in which we might intervene and make some changes. So what I'm going to be presenting to you today is basically some really Sociology 101 concepts to give you some vocabulary and maybe some ideas of things that you might want to do in your community. And I wanted to lead with this image because I have come to think about sociology as a lot like space physics. You'll have to hear me out here. But when you examine a planetary system, you have these complex dynamics of a plasma field and lots of particles whizzing around, and then this electromagnetic environment that is shifting and moving along with the planet. And your job, if you go study somewhere like Saturn or Jupiter, is to detect what's happening with the particles in that environment, to see like which ones are picking up a spin, which ones are ionizing, which ones are picking up a charge or discharging, and that's an indication of these underlying field lines and currents that are guiding and shifting along with the system. And so what I'm going to be telling you about today are what some of those field lines are, the ability to detect those field lines that are making a difference as the kind of currents in your community and others that are affecting how different scientists, as they move through the community, might have different kinds of biographical outcomes or different kinds of career trajectories as they move forward. So to that end, I'm going to focus my comments today on telling you 3 laws, 3 principles that underline or undergird social interactions, much in the same way that these field lines would direct particles and fields. One is status interaction effects. The second is the law of proportion. And the third is some principles of social networks. So I'm going to jump right in. And you can feel free to take notes because this is basically like Social 101 in 30 minutes or less. Okay, so let me introduce you to a common effect in science, which is called the Matthew effect. And this is what we would call a status effect that takes place in science. The Matthew effect says that the most famous name on the paper will get all the work attributed to them. Okay, lower status scientists and engineers will often be overlooked and their work will get attributed to their high status collaborators. Now, you may, laugh, but just think a minute. Last time you thought of a paper and you're like, oh, what was that? Who wrote that paper? And the first person you remembered was the highest status, like most famous person's name on the paper. That is what we call a status effect. That is a particular form of bias that takes place when we remember the higher status individuals in society and we continue to accrue status to those individuals based on certain forms of characteristic. Now, actually, the Matthew effect goes one further to what was identified as the Matilda effect later by Margaret Rossiter. And this is to augment this by saying that women who collaborate with men, whether they're married or unmarried to the men they're collaborating with, will typically receive less credit and men will profit more from their discoveries. And she found this across 100 years worth of collaborations where, teams went, received a Nobel Prize for the work and the woman was left out. So there's far more Rosalind Franklins out there than there are Mary Curies, for the record. But what was interesting is this even applies to the Matthew effect itself, because the person who did all the work on the Matthew effect paper was Harriet Zuckerman, who was married to Robert Merton, the more famous sociologist in the field. So the Matthew effect and the Matilda effect are what we call status effects, and status effects are well studied in sociology. Cecilia Ridgway, who was president of the American Sociological Association, is a professor at Stanford, talks about how status operates in society as a way of doing social sorting And what happens is that we incur a series of beliefs and biases that enable us to change our cognition such that we will apply those status beliefs to individuals that we assess. And we can see this in what we call audit studies, which are the resume studies. And you've probably heard of these, where sociologists will send out, 1,000 resumes that are exactly the same, and they'll just change one little thing on the resume, like the gender of the name or some kind of racial status of the name, or they'll put in, that these people belong to certain kinds of clubs that will imply a particular kind of social status. And that this ends up getting radically different evaluations that's not based on what's actually in the resume, but actually based on these status markers. One great example of this is very famous is what's called the orchestra study. This was, there was an issue in orchestras trying to get more, there just aren't very many good female violinists out there. And we just had these violin sections that were dominated by men, mostly white men. And Cecilia Rouse, who's now one of the major directors in the economic part of the Biden administration, actually, incidentally, became famous for conducting this study where she put up a screen and had everyone do the auditions behind the screen. And that actually made a big difference, because if you couldn't tell if they were male or female, you ended up evaluating just their performance and not based on status beliefs. And then they went one further, which was to put down a carpet so that you couldn't even hear the high heels as people walked out. And that's when you started to get more 50-50 representation. So these are all ways of evaluating how we apply cognitive biases that are acquired or associated with status in society, and that we apply those to different individuals as they enter into groups. Now, this can be this can be problematic in many ways. One is that when you're in a group that is a consensus context, where you're trying to achieve consensus, we often see that people are actually deferring to social status within that group, kind of latent status in that group. And so it can enforce a kind of silencing of conflicting voices, and can actually create kind of factionalization in those groups, as opposed to actually bringing groups together. So that's one thing to look at. Another that's very concerning, though, is that Ridgway's colleague, also at Stanford, Shelley Carell, identifies that constraints that we encounter in society will become transmuted into a biographical concept of a preference. So, as if you are a minority or a woman, or you're trying to move into these places where these status effects are being used kind of against you, you'll start to come up with narratives about how that really wasn't a thing you wanted to do anyway. So we end up having these biographical stories that are created kind of post hoc in response to general social issues and constraints. And this is where we also see the incorporation of those stereotypes by minorities themselves, who begin to acquire things like imposter syndrome, et cetera. Where things get really interesting for sociologists, though, is when status is combined, when you have more than one stereotype. And we call this a status interaction effect. So if you have a sort of high status principle and a low status principle coming together, what happens? And there's some really fascinating cases, actually, that once we start breaking things down and make it less binary and make it more multivariate, we end up seeing some highly regular, again, effects that are based on status. So we know that women who are placed into leadership positions experience a lot of social and situational backlash that they, again, might transmute into preferences. And this is largely because there's a stereotype associated with female in the West that is much more, much less domineering, but the association with leadership is that you're supposed to be agentic. And so those two things clash, and when those women experience a backlash. There's also backlash against men who are more sensitive, more sort of soft-spoken in their orientation. They'll be described as kind of weak leaders because they don't measure up to that leadership stereotype. But we also see some interesting interaction effects with things like sexual orientation and race. My colleague David Padula, also now at Stanford, has described, now at Harvard, has described that for LGBTQ men who are white, they will often experience a kind of like a sort of feminization in the workplace, or people will sort of hold them back, assuming that they're not high status. Whereas for African-American men, because there is a dominating stereotype that those individuals are more aggressive, that having that LGBTQ status perhaps mediates in some way. And so African-American men who identify as LGBTQ will be more likely to be successful. So these are, another one of my favorites is that another incredible resume study showed that white upper class men and white lower class women with exactly identical resumes with very few little signaling exceptions did better in elite labor markets associated with law. than white lower class men and white upper class women. So these kinds of interaction effects can be really powerful and really strange and really inspiring to try to figure out, like, what are the mechanisms going on there? We see status happening, but what exactly are those field lines and how are they combining and colliding? Two things that may be useful for you. We've identified particular ideal types in the sciences as well, in computing or in physics, that are highly discouraging of people who don't fit into those stereotypes. And if you're interested, there's a lot of literature there. And then there's also the fact that women and men who become parents are paid differently. And I'll just show you some of the data on this. But the women who are not married or who are young will make 90 to 96% of what men's earnings are. This was in 2012. But as soon as they start having children, that number starts moving lower, lower and lower. Whereas for men, it's the opposite. Men with children with high professional degree statuses, especially if they're white or even Latino, will acquire a kind of bonus and will even be paid extra because of the assumptions that they are being, good parents and they have to provide as their leader of the family. So again, there's no actual reason why, parents should be paid differentially based on gender, et cetera. But there are these status effects that are accumulating socially. So now that you know a little bit about this, and I'll give you these slides after so you can look some of these things up. But I want to give you some solutions because we actually don't have to work this way. There's implicit bias training tools or implicit bias tools that are online can actually be really effective as a calibration tool. So before you sit down to evaluate a bunch of candidates, do a bunch of those implicit bias test things just to get your brain kind of in that mode. It'll help you move away from status effects as you're evaluating candidates. I wouldn't use them necessarily to show you how terrible a human being you are, but you can use them to figure out, like, to just try to get that effect out of your data, basically out of your instrumental readings before you start treating it as data. Think about the Matthew and Matilda effects when you're doing things like evaluating promotions. Just knowing that that is a thing and it is measurable and demonstrated, I think, can be helpful. Having very clear promotional criteria is also extremely effective, and engaging in things like double-blind review and not always requiring self-selection will enable people to move past these status effects and status interaction effects and actually just be evaluated for their effectiveness in the job, which is, I think, what we're all going for. All right, so that's one way of looking at things, which is a little bit more culturally and cultural cognitive oriented to think about how status works in society. I want to shift now to another way of thinking about social groups, and that is to understand social groups in terms of proportions and proportional representation. So Rosabeth Cantor, who's a professor at Harvard over 40 years ago, proposed that when you have different groups and the proportions of minority representation shifts in them, you shift the social experiences of that group and of the minorities in that group. And she breaks this into several categories. You have uniform groups where there's basically no one's a minority. Everybody's in the same category, and you don't get any of the benefits of having a diverse team with lots of different information coming in and new recombinations of experiences and the kinds of things that actually we've now demonstratively shown, improve qualities of production and innovation and all those things over time. So you don't get any of that benefit if everyone's all the same. But if you add minority members to a group and you add less than 15%, you end up with a series of dynamics that she calls tokenist or tokenism. I'll explain that in a second. It is actually incredibly deleterious. It is deeply problematic for those individuals and for the group that they're in. So if you have minorities in at less than 15% representation in the population, you're actually in a fair degree of trouble for those individuals. If you can move that group number up to 30%, then you can start to reap some of the benefits of that diversity of those different ideas coming in. But you'll start to get backlash from the majority group until you get up to 50%, at which point just there's no minorities or majorities anymore. People are contributing and you actually get to benefit from all those different connections coming in. So this is why we've adopted in many different circles what's called the 30% rule. It's often talked about in business, that you should try to have minorities making up at least 30% at the different rungs of your organization, because when you have visible minorities, women, people of color in those roles at up to 30%, you can move away from the problems of these skewed tokenist groups and also the tilted groups towards actually reaping the benefits. And I'll just put up a couple of pictures here because I want you to note that, despite the fact that men and women are equally represented in the US population, give or take about 1 or 2%, they're not equally represented in places like the planetary science community, in places like tech, the tech industry, where in fact we see, in particular women in these cases, occupying, sitting right in that 15% spot, if not under that, then between 15 and 30%. And that's where we start to see extraordinary backlash against them, including things like the Google diversity memo. So here's what happens in skewed groups. In skewed groups, you get what's called tokenism, which is where that individual sticks out, like the O in this picture of X's. You can't help but notice the O. And this is one of the instructional videos that Cantor produced to explain this in business circles. So what happens is, it's not the tokenism. It's like, oh, this person got that job because she's the token woman or he's a token African American. That's the effect of tokenism. Actually, those people had to work extremely hard to get into that position, battling all the status interaction problems along the way. But when you get to that kind of a position, if you're at under 15%, people will say that about you, believing it to be true. So if you ever hear somebody say that, you should be like, maybe we're in a skewed or a tilted group. What's the proportionality in this group, right? If you're at 50-50, you probably are not going to hear that. But if you're under 30%, and definitely if you're under 15%, you will hear that. So there are some really devastating effects on individuals. So first of all, they're subject to stereotyping. They're asked to stand in for the entirety of a group. Well, you're the woman, you tell us what you want, in this group. They're also trotted out publicly as the representation of that group. Look, we have an African American, here this person is, and that person then has to take on extra additional burdens of not only being seen as the figurehead for their entire group, but also being the publicity for the group as a whole. And that makes other people in the group jealous, and they're upset that they're not the ones up there, and why is this person getting all the attention? When in fact, that kind of extra visibility prompts a kind of retaliation that's very scary and difficult for those individuals who are brought out over and over again that way. They end up becoming informally isolated from others in the organization. For a variety of reasons, they're not the same, but also because of this heightened visibility and because of this heightened publicity. And people end up testing them, like, which group do you belong to? Are you one of us or are you one of them, right? So these people find themselves placed in a very, very precarious and very difficult situation. So they end up lashing out. They'll often be micromanagers. They can become territorial. They can get, decried for not supporting their subordinates. She's a woman in charge. Why isn't she supporting all these women below her? Well, likely because that woman is in a tokenist situation. It is not okay or safe for her to do any kind of protecting of anyone else. So these elements then again end up being counted against them. So these are the kinds of things that we see again with respect to the proportionality of groups. And this changes as soon as you start moving that needle up. So once you get up towards 30% and then over 30%, these kinds of problems start to fall away. So that's why it's called the law of proportions, because we see this repeatedly. How are your proportions? I don't know very much about your specific community. I can tell you a little bit about the planetary one, but here's some numbers from, again, this is over about 10 years ago, so I'm sure this has changed. But I'd encourage you to find the numbers out for your community and also to break it down according to rank, because what we might see is that, women or other visible minorities might make up a certain proportion at a particular rank, but that will not carry through to the full professor rank or actually carry through in the department in general. So in the astronomy, in physics, and in the earth sciences, we still see a very low representation of women, but we also see low representations of Blacks and Hispanics with respect to the general population, and even with respect to the people who are, coming out with undergraduate degrees who could be moving forward into the pipeline. So when you see these problems, when you see these kinds of numbers, you should be thinking, that's that tokenism thing again. That's the law of proportions. So to combat this, you actually want to benefit from diversity. You actually want diversity in your group. It can be hard to have people in who think differently than you. It feels very strange. It's quite awkward. Every team goes through this thing we call forming, norming, storming, performing. And if you are all from the same background, you don't have to go through forming, norming, and storming. You've already done that. You can just perform, but you perform at a lower level than people who come through and actually go through all of that together and have to incorporate all these differences. They actually perform better in the long term. So you really want this kind of diversity. But if you're at under 30% of minorities at the level of your organization, you're going to be in trouble, especially if it's below 15%. You're going to get some really devastating dynamics. So those people are not going to get to move forward. They're not going to get to support others coming up. They're going to sort of stall out, and the advances you were hoping for are just not really going to be there. And you have to watch out as you start pushing those numbers up towards 30%, that there will be backlash dynamics. People will be like, why do we need this? Why are we doing diversity training? What's the problem with all of this? We have women here, right? So those are the kinds of things we would expect at that level, and they really fall away once you get over 30%. So it is about proportions, and I also recognize that you will probably not be able to hit these numbers with the workforce you currently have. So my suggestion always is to act with empathy, because when you have people who are in these situations, it is a devastating and extremely difficult situation to be in professionally, especially because science is a reputation-based economy. They are trying to protect their reputations going through the field, and they're trying to manage these very conflicting forces. They are stuck in these field lines. It is really, really problematic for them. So make sure that you can put, cultural things in place, or to have, mentorship, or to have some kind of empathy for those individuals, because they are under a lot of stress as they move forward. Okay, so that's the law of proportions. So I've given you these sort of cognitive bias stuff associated with status effects, and I've given you the law of proportions. And these are two very powerful laws, like electromagnetic field line laws, that are generating the field lines in these different fields. And there's a third, though, and that is social networks. And this is another way of thinking about social fields, social communities. So we can think about them in terms of culture and cognition. We can think about them in terms of demographics and proportions, or we can think about it in terms of interconnections between network nodes. And that's what social network theorists do. They look at communities of people, and they look at the social ties between members of those communities. And there's a couple of things that we know about how humans work in groups. One is that there's a principle called homophily. This is a very powerful law. It might as well be gravity, that birds of a feather will flock together. People like to be with other people who are like them. So naturally occurring social networks that don't have any other kind of interventions in them display a lot of homophily and a lot of barriers to entry for people who don't kind of fit into that group. But social network analysts are very interested in what happens when different groups start to come together. So they're interested in what they call brokerage ties, which is when you bridge networks together. So imagine, the earth science community gets together with the helio community, and then you start having these brokerage ties where you have a lot of innovation as we start thinking about heliophysics in the space around Earth, right? That's a kind of brokerage network, and that's the power of things like these kind of interdisciplinary communities that sit between these different networks. We also know that you can have stronger ties and weaker ties. So strong ties are the tightly connected members that you pay a lot of attention to, spend a lot of time with. Weaker ties are further removed, or maybe 1 or 2 or 3 hops away. And we actually know that we get more opportunities and information from weaker ties. Within strong tie networks, they become too consolidated, and you just get like an echo chamber. So you end up only hearing the same information. You might be noticing that this happens on your favorite social network of choice, as opposed to when you actually get information coming in from 1 or 2 hops away from weaker ties is when you start getting new ideas. Now, interestingly, social network analysts are not just interested in networks because they're networks. They're interested because they're maps of social capital. That is how socially connected individuals are. This is another way of measuring social status to a certain extent, but it's actually really a question of like who's in and who's out, and that different networks and powered network relations will work in such a way to maintain strong degrees of social capital among individuals who are deeply socially connected across more than one network space. Okay. So there's a couple of things that we know that happen in networks that I want to tell you about because they happen in science a lot. The first is called the paradox of meritocracy. And the paradox of meritocracy has been experimentally shown by researchers at MIT that show that in organizations that determine advancement through criteria of merit only, there is an increased disparity between gender, between women and men in senior roles, and increased disparity in this case, it's pay, right? And it's because what people are doing is using reputation and similarity to promote and recruit based on fit. So what they are doing is they're relying more and more on relationships, reputation, and social capital to determine merit, as opposed to formal rules for advancement. So the more the less sort of structured your group is, right? The less structured your rules for advancement and your rules for a promotion that are actually merit-based are, the more you're going to rely on your social networks. I know this person, they're a friend of a friend, they studied with my colleague. Those are people I trust, and I'm going to use those relationships of trust and reputation and social capital to determine that this person should get the job or should get the bonus or should get the grant or whatever. So this dominates especially team assembly and startup culture, but it's also very powerful in the sciences as well, because if we don't pay attention to the fact that we will double down on our stereotypes, actually, when we're in these kinds of situations, then we're going to end up increasing the disparities between men and women in the field and between visible minorities and whites in the field. I also want to let you in on an interesting secret, which was discovered by Ron Burt, who's a towering figure in social network analysis. What he discovered in the 2000s, he was working with large data about a particular corporation, and he couldn't figure out why it wasn't making any sense, like why the networks weren't working so well. And so he started looking at them by gender. And what he found was that gender really mattered for the accrual of social capital in a network. That social capital accrues differently based on gender, and then this has also been shown based on different racial groups and organizations. So what he found was that the people that were kind of members of the boys club, which were white male networks, and that not all white men belonged to these networks, but there were some very, very powerful networks, that if you belonged to those networks, you could receive twice as many job leads as people that were just networked with other women or minorities. He found also that women's networks would provide like local advantages because they would provide information locally, but they couldn't translate that necessarily to social capital more broadly because the networks were too closed. So they had to have somebody in a brokerage position between them in the women's network and the more powerful networks. And we call this position the work uncle. And the work uncle is the more powerful man who can kind of support subordinate women's careers and can give information, like pump information down into those minority networks. And that women can kind of borrow that social capital and that social status as they move in the community. And this is actually what I found when I studied planetary scientists. Many of the women who were able to get ahead in planetary science did so, first of all, because they were part of a networked group. So they weren't tokenized, they were part of a network group. So they had a women's network, but then also they were taken on by somebody in the field who was quite powerful and well known as a powerful white male in the field. So they had work uncles. Women themselves don't really get to do brokerage as effectively as the men do in those positions, or as more powerful social status actors do in those positions. The network has to be highly diversified before they can do that. And that's largely, again, because of the tokenism problem. And again, because moving between networks is very problematic, and it kind of puts you in a situation where you're going to have status incongruities, like role incongruities associated with status effects. And you're also going to be tested for loyalty. So those are two positions that these people don't do very well in. We also note that young men are disadvantaged in networks of primarily senior men, but they will actually make up that disadvantage as they get older, and the women who are not in those networks do not make that difference up. So these are some things we know about networks. We know about how humans work when they're in social groups, that they connect together with other humans who are like them. They like being with humans that are like them. They will do a lot to keep humans that are not like them out of that group. They will reward humans that are connected to them in some way or share characteristics with them in some way, with resources and with information and with opportunities. And that as minority networks cluster together, if they are too distinct from more powerful networks, they will not experience any of those benefits. And it's only through some kind of bridging tie that they're able to get, the information is able to move more and more freely, and that you start to break those networks apart and diversify them. So there are some ways to combat this if we know this is how humans work. So one is to reach out to weak ties. We tend to tap our closest friends and colleagues for information, especially under COVID, where we have not been able to walk down the hallway and hear conversations or start things up or say, hey, did you know this grant is coming down the line? Now we really are sheltered from our weakest ties, and the weak ties are where the new information is coming from. So we actually need to reach out one or two network hops away, ask for someone else who that person knows. And this all comes from Mark Granovetter's early work, again, from Stanford in the 70s, where he noted like, you're more likely to, you're not going to get a job from your uncle, but you'll probably get a job from like your uncle's neighbor, right? It's that weak tie, that information going through those ties that's going to help you. So go to people on the periphery of your network for recommendations. Help people that are in those bridging roles between those networks, because that's where the innovation is happening, but it might also be very difficult to recognize their work. And one of the things that Bert found is that those bridging positions are held by both the highest authority people and also highest status and the lowest sort of status people as well. When I worked on a mission, I saw this with interdisciplinary scientists who were very powerful, very senior men in the field who could work with more than one instrument. No one else could work with more than one instrument unless they were grad students cobbling money together from multiple PIs. So both the highest and the lowest on the social totem pole were in those bridging positions. So you want to make sure that those bridge positions are getting the support that they need, and those individuals are getting credit for the innovative work that they're doing. You also want to support minority networks. So these things like the Association of Black Physicists or women's networks within your communities are actually really important, so that those people know each other, so that they're supported, so that they're in a cohort, so that they're not tokenized. But you need to create strong and robust bridges to those communities. So you might want to sort of reach out to them to ask people in those communities for recommendations of who should sit on a panel, et cetera, who might want to join your mission. And then you might yourself also want to actively be the work uncle, to stand up for them when there's a problem with tokenism, and to make sure that there's somebody there making sure that information is getting to those other networks as well, so that you can diversify. So I've talked about status effects, the law of proportions, and network effects. And these are three ways that sociologists, when we look at social systems, are able to make sense of the underlying mechanisms for the reproduction of social inequalities. Why inequalities reproduce themselves over time is a huge challenge to sociologists. And it's in looking for these field lines that we're able to say, oh, this is how this community is working. This is the way the plasma flows, and this is why. And if we made these kinds of tweaks here or there, it might work differently. And I think there's a really powerful implication to consider for your community as well. And this is where I'm going to adopt a different physical metaphor and tell you a little bit about Enceladus, which is, of course, the moon around Saturn. Enceladus is a water moon that is surrounded by an ice sheath, and it is spewing water all over everything in the Saturn system. It is blowing water all over like Mimas, and all these moons are just getting pockmarked with water, and it's creating an additional ring around Saturn, the E-ring, and it creates like auroral effects. It's interacting with the magnetosphere, and like, won't Enceladus just shut up, right? Well, Enceladus is not going to stop doing that, because Enceladus is doing that because it is trapped in a gravitational well between Saturn and its orbital resonance with Dione. And because of that, it is caught between very powerful gravitational forces. And the only thing it can do is tear itself apart under the strain. And what I would suggest to you is what I have just described are three sets of powerful like gravitational laws that are going on in your community and other communities as well, largely unchecked, right? And in those situations, you will find individuals who will become Enceladus. They will be the ones who blow up. They will be the ones who can't take it anymore. They will be the ones that are put in untenable positions. They're not credited or recognized for what they did on this paper. They're not, they're being trotted out for award after award, but they're not being invited, to do anything else with their colleagues. They are, they're sheltered, and they're never given any credit or any information about what's going on. Like, these are the people that are going to be suffering from those effects, those sociological laws that I told you, and they're going to be in situations where they have to explode. And I saw this on one of the missions I studied, where a woman who was in a very powerful leadership role said, my job is to represent my team. So no one's listening to me. I get louder. They start looking at me. They're like, what a bitch she is. And I just want to say, I'm sorry, I have to act this way. You made me this way. If I don't act this way, you don't pay attention to me. You develop a reputation. And again, I said this before, but the sciences are reputation-based communities. And so individuals who are moving through are trying to do science, but they also are trying to manage their careers, right? And in this career arc, they have to kind of make their way around these very complicated social dynamics that are occurring behind the scenes. So my advice always, again, is to act with some empathy, to recognize that many of the people in your midst who might start to acquire reputations are possibly in Enceladus-like situations. And additionally, to take some actions to confront or to push back against some of these quote unquote natural laws, so that we can use bias training or articulated procedures for advancement to manage problems with status effects, as well as to manage to push back against the paradoxes of meritocracy. We can do things like try to enforce a 30% rule at every level of the organization, and when we can't do this, when we can't do that, we can do what we can to support people who are in those lower proportional roles. We can tap our weak ties. We can create network bridges. We can open the networks for more minorities and for more innovation. These are the kinds of things I think we can do as communities if we work together, and if we recognize precisely which social forces we are working with. So I'm going to close there. I will promise you that there are many pages of references associated with this presentation, and I'm happy to take comments or questions here as well as on Slack. Thank you.
Thank you, Jenna. That was a great talk. We have a lot of questions in the Q&A, so I want to get to those to make sure we can get to them on time. The first one is, what do you recommend for people who are in a position of being a tokenist situation? How possible is it for someone who is in that kind of situation to help move more representation to an appropriate level?
This is always my hardest question. I am so sorry. My heart goes out to you, because that is a really horrible situation to be in and to put anyone in. I think one thing to do is to get a network and get a work uncle if you can. And if you can't, then get out of that situation, because it's not going to necessarily improve. So the women that I saw who were very successful, the white women I saw who were successful at NASA, I should say, who avoided tokenism, were ones who had very, very strong networks around them. They were the women who met as technicians. They were sort of starting in their careers. They became friends throughout, having kids, et cetera, and they are still each other's closest colleagues. And they were the ones who were able to avoid tokenism because they kind of moved up together. They kept appointing other people up with them as they moved up through the ranks. The women who were appointed directly into powerful roles were not so lucky, especially if they had no support. Additionally, the women who were appointed in those roles who did not have a work uncle were really left out to dry. And this happened when, for instance, one woman who was in a powerful position did have a work uncle and he died, right? And there was no one there to kind of stick up for her or to fight some of the battles behind the scenes or to ensure that everybody knew she was just doing her job and not being a bitch. So I would suggest for those individuals I would suggest that the work uncles and the networked communities are probably the strongest ways around that. Otherwise, you need to leave. And if you're not in a position where you can really appoint new people up, you need to make it clear also to the other members of the community you're in that that's not going to work for you.
Okay.
Yeah. Sorry.
So, yeah. So the next question gets to a section earlier in your talk. It asks, did you investigate, and if so, did you find a difference between areas where publications tend to list the main contributor first, like in our field, and those that go strictly by alphabetical order, or those that list the instigator of the work first or last?
Yeah, it's a really good question. I think you're talking about the Mertens stuff, right? About the Matthew effect and the Matilda effect. I believe the original work was done with a variety of different fields, and so it wasn't necessarily limited to, because I know author order is really specific field to field. I think this has now been subject to much larger and broader ranges of tests because we can now do things like download the entire web of science and figure out what the underlying social structures are there. So I can have a look for a couple of publications that would show that. The interesting thing though is that it's not actually about who the first author is, and that's the surprising thing. And it isn't even who the last author is, because in some fields the last author is the most important. It's who the highest status author is, and that's the person who typically acquires the credit. So that's the person who you remember. And if you think about this, our monkey brains do this for a reason. Like we come from these little tribal monkey groups in which like high status monkeys are the ones you've got to pay attention to, and they're the ones that are managing resource distribution and so on. So like it's important for you to know who's high status. Like that's key critical information. It's just such critical information that it overwrites the participation of anybody else. And those people who tend to be lower status socially are the ones who occupy minority positions, whether it's female or people of color or graduate students. They tend to be not as remembered. So it's just a thing to keep in mind. But yeah, you can absolutely have a look for the Matthew and Matilda effects and some of the larger, billion science publication stuff. Yeah.
Okay, thank you.
Yeah.
Okay, so the next question is, it seems that there's a catch-22 with the 30% minority representation rule. If you're an organization with low minority representation and you're trying to get to 30%, the easiest way to get there is to add people based on their minority status.
Yeah.
However, this just reinforces the stereotype of tokenism. So assuming it's possible to get to 30%, what's the most ethical way to get there?
Great question. Cluster hiring. Cluster hiring. If you're always looking for the one person, it's going to be the highest status person every time. It's going to be the most well-connected, like loveliest white guy you can find. And I have nothing against white guys. I've married one. They're great, but they're not always the most deserving of all the things that are thrown at them, given that there are other people who are also deserving of many things that are not thrown at them. So what I would say is, and I know this is hard in funding environments where you don't always get to cluster hire, where if you just go in and you want to ask for like 5 FTEs, your dean of faculty is going to fall on the floor with a heart attack. But trying to figure out how you can hire more than one person at a time will always open the door to saying there can be other candidates here. It's actually really surprising and you should try it. And then the nice thing about it is that actually all those people are there because you've made some very clear criteria for them getting there. Hopefully that's the other way to do it. So write those criteria out in advance so that you have the checklist and then you have multiple positions. Then the other thing to do is to look at your checklist, because your checklist could be oriented in ways that's turning some people away. So we know also that members of a field that are in the higher status positions will kind of flock to the kind of centers of the field, like the central questions. And many women and minorities will be attracted to the quote unquote peripheral questions in the field, like the ones that are like interdisciplinary, for instance. If you're defining the problem too narrowly, you're not going to allow the people in who have other kinds of expertise, but who actually have a lot of expertise in the topic and may have additional expertise because they're connected to other communities. So those would be my 3 answers. 1 is cluster if you can. 2, write all your requirements out. 3, double check those for making sure they're inclusive of people who are really bringing in new ideas, because that tends to be where those minority candidates are. I hope that helps.
Okay, looks like we have time for 1 or 2 more here. So let me get to so the next question would be, it was a very nice talk. One of the issues with representation is that a small number of people are asked to serve on many community panels, etc., and so get overloaded. I think that one of the jobs of a mentor is to help mentees avoid getting overloaded with services so that they can do the core work to advance their careers. What is your perspective on this matter?
Yes, this is a challenging one, and it really gets to the heart of tokenism, right? Because this is that additional visibility. Oh, we need a such and such person to serve on this committee or whatever, and you're that one person. So yes, I think, and this is why, getting back to the question about what do you do if you're in a tokenist situation, is get a work uncle, get mentors, and get a community. I believe that is a powerful role that mentors can play, because they are effectively that kind of work uncle who can help the person have some perspective. But then the other thing to do is to recommend others. I mean, this is also where having networks is important, because that load can be shared. And then also diversifying the network somewhat so the load can be shared. So if it's just one person who has this particular social status, they're going to get flooded. If that person can find others who have similar kinds of social status, then they can say, I can't do this, but I recommend so-and-so, right? And that enables them also to protect their reputation as they gracefully turn down the opportunity. And I think that's also where mentorship can play a really key role, because the other kinds of mentors I saw were the mentors that were in these minority networks as well. The women who made it, who were the technicians who made it up the ranks, were promoting and bringing in other young women to sort of, be the next generations. And so they were playing really key and important mentorship roles there. So the mentors can always be looking kind of up and down the chain of like, who might be another person that could be asked for this role, et cetera. And then individuals joining these broader allied diverse communities can also then say, oh, 1 or 2 network hops away, you should ask this person instead. I hope that helps. It's always complicated when you're in that position, but definitely, sit down with your mentee and say, with whatever stage in their career they're at, look, this is what we need for tenure. This is what we need to make sure you have for tenure or for this next promotion or for advancement. So all of the energy should be here. And, here's how much time you have for this other stuff. And let me help you with that other stuff to make sure that you're not overloaded.
Great.
Yeah.
So we are running out of time here, but I want to ask one final question because it seems like a lot of people want to discuss it. How can we as a field move past the work uncle phenomenon and help ensure that mentors who aren't senior, white, and male can also have an impact? And how can their mentees succeed?
Yeah, so the work uncle phenomenon really refers to the fact that that happens in communities where the most powerful networks still are white, male, and quite senior. But one of the things I pointed to talking about this other group that I saw at NASA was these women who really formed their own networks, like a shadow network at first, and they started really bringing new people in who kind of filled in that network and awarding opportunities that came to them to those people as well. So they became almost like work ants, right? Because that community started to become more and more powerful. So really the work uncleness is just a question of making sure that somebody who's in a powerful network is the person who serves as the bridge to make sure that information flows into less powerful networks. And that the person from the less powerful network isn't the person who's expected to interact always with the super, super senior powerful people, because they will not really be able to do that very effectively. So I think, again, these issues disappear once the networks are highly diversified. If you have more representation of women and other minorities in these networks, you don't have to see the uncleness happening. I do think, though, that the work uncle can be powerful for those men in the field who really want to be allies. And it's very hard for them to know what can they do and what can they do to support. If they believe in diversity, if they believe in the careers of these individuals who are moving up, they want to see the field change. That work uncling is a very powerful and effective thing that is available to them to do. So I agree, it would be nice if it weren't just like it's all dominated by a bunch of very senior graybeards. That there's a lot of things you can do in your community to start to shift that, but having the senior graybeards on board is going to be important to make sure those networks can start moving up, those individuals have more visibility, they have more opportunities, and the networks start to diversify more generally. So that's what I would offer there, but it's a long-term process, and I'm happy to keep the conversation going if this is something you're interested in.
Great. Well, thank you. There are a few questions we haven't gotten to, but I will copy and paste those over to Slack and we can kind of continue the conversation there.
Perfect.
So yes, thank you. Thank you again. And I'll hand it back to Adam.
Thank you, Mike, and thank you, Janet, and thank you everyone for your patience going through an extra 15 minutes here. I just have a couple of remarks. So yesterday's plenaries are available for download, as well as David's this morning. You can find all of that on the VGEM website, as well as talks that were uploaded in several of the concurrent sessions. Please vote. You can find the voting link on the VGEM website. And if you haven't already, please, if you weren't here yesterday, maybe you just joined today, please get over to the Gather Town. The links to that are also on the VGEM website. You can find them at the top. And there you will find a photo collection that's around 23 minutes long to have a look at in the main area. And also you will find a voting box, and you can have a look at the posters from yesterday and for the ones that have been uploaded for Thursday. And just finally, we will have another Sam Bingham Community Cares Initiative session this evening at 5 to 7 p.m. Eastern Time. Please refer to the timings in the schedule. The timings on the SBCCI page need to be updated. And so I think that's it. So everyone have a great